You're welcome. Thank you for the kind introduction. The topic of my talk is physics of failure-based model and model-based reasoning to facilitate condition-based maintenance and predictive maintenance processes. I would initially talk a bit about the background of the company, because that's necessary in order to find out what we are doing and how we are doing that. It is in essence knowledge-based methodology applied then to fleet analytics for O&M optimization. A few words on the Romeo project as mentioned, and I would finalize with benefits and further potential. Uptime's vision is to make technology reliable, and in order to do so, we develop consulting and software solutions for our customers. We work across industries, cross-functional, and our job is to make our customers the reliability leaders in their industries, which are automotive and rail, wind and photovoltaics, heavy-duty agriculture. As mentioned before, I'm going to talk a bit about methodology. A lot of our activities refers to product development, and the basic question in that respect is, how do all the different activities which are executed during product development, how do they contribute actually to system development? Our approach to this question is, we analyze initially failure potential of all the components of such a complicated mechatronic system, and a list of relevant failure mechanisms results from that activities, which we in a second step model with respect to the damage kinetics as a function of observables. An example would be cavitation, which is a failure mode occurring frequently in pumps, and cavitation occurs whenever the speed of the water is high, the system pressure is low, and the temperature is high. That means as soon as we know about a certain failure risk, we know from the nature of that failure risk which type of input we need in order to assess a time series of a certain load condition, meaning a load duty cycle with respect to damage kinetics. That means we are able to transfer the time series of critical operation condition to a time series of damage kinetics. And we apply these models, the list of models, to all the different types of activities in order to find out how efficient is a validation process. When we talk about monitoring analytics of system, we extend this analysis to check whether there are any evidences to be observed with respect to a certain failure mode, whether we are able to detect deviations for early warning, how can we diagnose root causes, how can we predict remaining useful life, how would a corresponding functional solution look like, and how we could automate that process in order to make it actually happening in an industrial environment. We did this sort of activities for dozens of different projects, and what turned out is that a certain generic type of knowledge base resulted, which can be used as a common resource for risk assessment and problem solving. This knowledge base is, let's say, a library of failure modes, which refers to component classes, assigns various generic failure modes to these component classes. The concentrate and the core of the whole activities is the root cause analysis. The root cause analysis indicates which type of degrading or damaging operation conditions are to be expected, and from this analysis it's possible to identify the physics of failure-based damage model, which later on can be used to predict remaining useful life. That's one aspect, and the other aspect is to identify state detection, indicating a certain deviation of a certain component from expected values with respect to a certain type of failure mode. We, as I mentioned, identified and developed these activities for product development, quickly realized that it's also useful for quality and that it's also useful for maintenance. So we have, for the full life cycle, we have quite a robust and comprehensive database, which we can use in order to accompany the complete life cycle with our methodology. For the topic of fleet analytics, I have outlined how we would approach that topic. We start with the classical structure of the knowledge base, failure mechanism, root causes, operation boundaries, observables, and identify for these aspects what is necessary in order to detect, in order to diagnose, and in order to predict. For detection, indicators and observables are necessary. Enter into detection algorithms, which delivers alarm and warning, which gives also rise to diagnosis algorithms, which identifies the root causes based on the library which we have here. And with the root cause, we are able to identify the corresponding lifetime function, which identifies something like remaining useful life, for example. That means the route to predictive maintenance comprises of 3 steps. The first is detection, the second is diagnosis, and the third is prognosis. And a typical case is a wind turbine, as mentioned already by the chairman. Typically, we find a certain amount of instrumentation plus information from the system controller. There might be something interesting, and typically for state detection, we compare such a measured time series with system response models, and the time series have to be compared for relevant observables. For a bearing temperature, which is indicated here, the temperature is for bearings is a relevant system parameter because it indicates whether there is any heat dissipation going on, which is anyway always indicating a certain deviation from the operating condition. And that means with the aid of system response modeling, we are able to identify at a very early stage with high sensitivity and low frequency of false alarm and deviation from the expected system behavior. Another example would be an electronic grid, as we have it for the connection between the turbine generator and the grid. And we are able to simulate the grid behavior. That means we are able to simulate the output of voltage output as a function of the voltage input. And the question is, let's assume there is a failure in the central capacitor. Would we be able to identify that type of failure by the pattern of the output parameters, which you can see here? This is perfectly feasible. So we are able to identify observable failure patterns for a certain type of failure. And with these observable failure patterns, we enter the model-based reasoning engine, which allows us to identify corresponding failure modes. The example shown here indicates that over time, there are some observations, namely reduced power and generator derating. And what we do not observe is also most interesting, namely blade misalignment or curtailment. These observations are used by a model-based reasoning engine, which comprises the relationship between root causes and observations, and the reasoning engine does a comparison which type of failure reason candidates are compatible with this set of observations. The only one which fulfills this requirement is insulation aging, and the corresponding advice is check of the winding insulation. This would be the advice to the service guys. And the question which remains is, how fast is that necessary? So how urgent is that activity? If we wanted to answer also this question, we have to refer to lifetime function modeling. With respect to thermal aging, the standard scientific approach is Arrhenius. The Arrhenius function links the aging kinetics to the temperature of that component. That means as soon as we know the generator winding temperature time series, we can transfer this input series to a damage kinetics series, which is indicated here in this bottom sheet, and the integration of that time series delivers the time consumption, delivers also the failure probability, and in essence the urgency of a corresponding activity. So from the process point of view, irrespective of the type of industry we are talking, we start with a time series. Time series is used as a basis for uptime harvest. Uptime Harvest delivers with the reasoning engine issues and diagnosis. And this diagnosis is used in order to set up standard service activities, which are executed by the service staff. And ideally, we get the feedback from the service staff in order to make our system more reliable and more sensitive to the expected failure modes. One application of that activity, apart from customer applications, the Romeo project. It is a 5 years project on reliability, O&M decision tools and strategies for high cost of energy reduction in offshore wind industry. It's a consortium of 15 companies which cooperate in a EU-funded project. And the job of Uptime engineering, that aspect, is to make, globally speaking, to make information useful. That means the input for the whole activities are SCADA and sensor data and events data, which are stored in a central database. And there are various analytics activities which refer to this database. The analytics are both from a physics and failure point of view, from an event processing point of view, and also from machine learning point of view. They all use the same sort of database, and they all generate results, and the results are uploaded to Harvest. And the job of Harvest is to set up a joint O&M platform, means communalize all these type of results, which already is executed, integrate the data from these multiple sources, which is also executed. And the third job is currently under execution, analyzing, combine this information. And the point here is that from a large variety of different activities and different results, the operator, the fleet manager, expects one single recommendation. For example, how urgent is it to replace the generator once we have an indicator, the indication that the temperature is becoming a damaging effect on that. This is what Uptime Harvest is currently executing in order to trigger CBM activities, facilitate the CBM process, which has already been analyzed together with those project partners who execute actually fleets, and establish a comprehensive reporting system. Benefits and further potential. Last slide in the presentation. Benefits of the model-based approach. According to our experience, we have quite a good acceptance of the engineering communities. We need just only limited input defined by the actual failure mode. We have straight and generic process, and further potential is synergies with other methods, as in particular investigated in the Romeo project. Design risk focused system supervision is possible, and product design and protective control is possible. That's it from model-based analytics. I'm open to your questions.
Thanks a lot, Franz, for the very interesting talk. And of course, as usual, we are open to questions from the audience. You can use the chat, you can use the Q&A tab. I have one, and I think you can see that coming. So you talked about possible synergies with AI and data-driven methods. Can you elaborate a little bit more on this topic? I spoil that we have a whole section of this talk dedicated to hybrid models.
Sure, I expect a lot of synergy. We in the past used, let's say, data-driven or purely statistical models when we did failure analysis, because in terms of failure analysis, it's often so that you do not know about the mechanism which actually led to the failure. While in our physics-based approach, we assume to understand how the different types of failure modes work. In reality, this is the case for the majority of failure modes, but there is always something else, something which is hidden, something which we did not experience in the past. And in particular, for this type of question, which are very relevant from a reliability point of view, I expect that we will find a lot of potential.
Thank you. Do you see in the near future expert systems succumbing to the advance of AI-based methods, or do you think that they will just live together and be more powerful together?
Yeah, I think that the combination of expert systems with deep learning or purely statistical approaches has a large potential, but I don't see a lot of activity in that respect. Maybe I'm not familiar with what's going on, but at the moment I do not see very much. But we are currently starting a project in the rail sector, and our partner there has done a lot of machine-based artificial intelligence methodology in the last 3 years. So I expect that this project will give us the chance to check whether our expert system-based approach and their artificial intelligence-based approach show some, let's say, concrete potential for improvement of the results.
Thanks for this answer. A question about the impact of the Romeo project on the transition to sustainable energy. So you said that one of the most important benefits of condition-based maintenance is the reduction in operating costs. So can you give us some intuition about what is the impact in the price of energy? I mean, how much the CBM can save in terms of euro per megawatt hour produced by a wind turbine?
Very difficult question because it refers to the future. But anyway, there was an initial assessment of the reduction potential, and it, as far as I remember, it resulted in a value larger than 10%, which is huge. And it is, on the other hand, necessary because, in particular, with respect to offshore operation, there is a large risk of losing time and a large risk of extremely high repair costs, which is all much more severe than in onshore operation. Therefore, these activities were started by large utilities, actually. So they actually intend to practically use the results of this project. So it's not just of academic interest, but they intend in detail to apply let's say the powerful and the successful methods which turn out during that project.
Thank you. We have questions from the audience, and I'll use a little bit of the lunch break, just a couple of minutes to try and answer those. So Anna is asking, in my experience, the main issue of CBM and predictive maintenance is the lack of data with reliable labels. Have you experienced this? How can you overcome this issue?
Yeah, I know. I understand the question. Typically, the reliability approach is setting up a reliability matrix which consists of fit rate or something like that from the literature, which we do not do. And the background is that when you look at the libraries for fit rates, it turns out that depending on the source, you can get a difference of 2 or even 3 orders of magnitude, which is, from our point of view, absolutely useless. On the other hand, we have quite a solid and comprehensive set of damage models which describe the correlation between the actual load condition and the expected lifetime of a component. And in some cases, we can get the lifetimes from literature. In some cases, we can get it from the manufacturer. And sometimes we can even derive it ourselves, because as soon as we know about the insulation material of the generator, we can make quite a robust a prediction of the lifetime for that particular insulation materials. But the question is understandable and correct, because we don't talk about just a few failure modes. When we talk about the wind turbine, we talk about something like 150 different failure modes. And correspondingly, for each of these failure modes, we need the, let's say, load capacity input from literature, from experience, from testing, etc. It's definitely a big job, sure.
Nice answer, and really opens the mind on different approaches to the problem. So I say the audience, feel free to keep in touch to get in touch with Franz if you want to ask more questions. Of course, we have Another question from Braulio. To scale this type of knowledge-based approach, is data standardization important? How large should the scope be?
Sure. Data standardization is absolutely essential. A large amount of all our activities is with data standardization, with data quality. The data process is something which most of our customers do not apply, at least to that amount which is necessary in order to deliver a high level of input data, which allows for reliable statement with reliable results from our activities.
Okay, one last question. I'll tweak a little bit the one which was asked by the audience. The question is about uptime harvest. How can you create the knowledge base? Which kind of inputs do you need? You already partially answered to that. But there is also a second part of the question, which is the knowledge base available across different customers? And my addition is there any chance that it can be made public in the future?
Mm-hmm. The knowledge base is actually the core of the company. So we have established it and we have developed it over the last 10 years as a, let's say, side effect of different projects, problem solving, failure analysis, system supervision. So it is the treasure of the company. And we share the knowledge base with our customers to that amount which is necessary and useful for a certain type of project. For example, if we start a project supervising offshore wind turbines and the wind turbine contains a transmission, of course, all the information and knowledge which we have about transmission is shared with that particular customer, but not with the public.